Hello, and welcome to the first ever episode of Quotient Space. In these videos, I'm going to try to explain non-Euclidean geometry. And if that topic sounds big and scary, don't worry. Understanding the basics is not as hard as you might think, and these videos are designed to be accessible to anyone with high school level geometry knowledge. In this first video, I'm going to discuss the postulates or basic assumptions of Euclidean geometry, and how those for non-Euclidean geometry differ. In the next two videos, I'll discuss elliptic and hyperbolic geometry respectively, which are the two categories of non-Euclidean geometry. So if you feel like you're pretty solid on your Euclidean geometry, you could skip to the next video. Anyway, let's get into it. So what is Euclidean geometry anyway? Well, it's the geometry you've all been learning since kindergarten. Familiar geometric objects like triangles, squares, lines, cubes, and spheres are all Euclidean geometric objects. Euclidean geometry is the geometry of the flat 2D plane. It's the geometry of the three-dimensional space we inhabit. Although these coordinate systems weren't developed until years after Euclid. So, who was Euclid anyway? Well, he was a Ptolemaic-era Greek geometer who, around 300 BC, compiled the most advanced geometric theories of his time into a text that he called Elements. Now, I don't think it's an exaggeration to say that Euclid's Elements is one of the most important mathematical texts ever written. It served as the basis for the geometry that we all learn today and was an instructional text in the Middle East and Europe for over 2,000 years. In Elements, Euclid constructs the geometry that we all know from a series of basic principles. You can't prove something from nothing, so every logical or mathematical system needs some core assumptions. These are called postulates, or axioms. Euclid defined a series of postulates for geometry. They are: 1. 2 points determine a line. 2. 2 points determine a line segment. 3. 2 points determine a circle. And 4. All right angles are equal. There's actually a fifth postulate of Euclidean geometry, but it's not on this slide for some reason. Oh well, let's start with these four. One thing to note is that I have paraphrased slightly. The actual postulates are a little longer than this. But they're all very simple geometric concepts, so I'm able to reduce them to these pithy 4 or 5 word phrases. You may have even heard some of these before, like 2 points determine a line. Although Euclid's first postulate is often misquoted as 2 points determine one and only one line, which is not what it says. But it really says 2 points determine at least one line. Special thanks to Euclidrake for helping me make this point. I think this is important because while it is true in Euclidean geometry that 2 points determine one and only one line, we can actually prove the fact that the line between any 2 points is unique. We don't need to assume. I use this example because it illustrates an important aspect of writing postulates to begin with, which is to keep them as simple as possible. You don't want to assume something that you can prove. Minimize your assumptions, maximize your conclusions. That's how these systems are constructed. An important upside of this approach is that this postulate, as written, holds for both Euclidean and non-Euclidean spaces. It's true in all non-Euclidean spaces that 2 points determine at least one line. It is not true in all non-Euclidean spaces that 2 points determine only one line. The other postulate that I think gives some people trouble is number 4. All right angles are equal. Now, you might say, aren't all right angles 90 degrees? And isn't it obviously true that all 90-degree angles are equal to all other 90-degree angles? First thing to note is that degree measure is actually a pretty sophisticated concept. It didn't exist in Euclid's time. Nowhere in Elements does Euclid make reference to degree measure. And degree measure as a concept is actually predicated on this postulate. So it's not that we know all right angles are equal because they're all 90 degrees. We actually know that they're all 90 degrees because this postulate says they're all equal. We can't use this fact a priori to prove this postulate. Now you might ask, what does it mean for an angle to be a right angle if not that it's 90 degrees? Well, let's see what Euclid has to say on the subject. Euclid says 2 intersecting lines form right angles when the angles on either side of the intersection are equal. I'll use an example to demonstrate why we really do need this postulate. Consider this diagram. And apologies in advance to anyone who's colorblind. I did not design these diagrams to be colorblind accessible, but color is never the only distinguishing feature. So the 2 marked angles here are on either side of an intersection and they're equal, or at least they're supposed to be, pardon my drawing skills. So are these right angles by the definition above? Why or why not? Think about it for a minute. I'll wait. Okay, that was a lie. I actually won't wait, but feel free to pause the video and think about it. If you do, you'll probably come up with something about how this says two intersecting lines form right angles when the angles on either side of the intersection aren't equal. And that V shape isn't a line. Is it? How do we know that this isn't a line? What have we assumed so far that says that lines are straight? Euclid says that a straight line is a line which falls evenly with the points on itself. A line that falls evenly with the points on itself. And if you're interested, he defines a line to be a breadthless length. So a straight line then is a breadthless length that falls evenly with the points on itself. Does that sound a little vague to you? Yeah, me too. The truth is that despite Euclid's best efforts to codify our intuition on this, we really haven't assumed anything so far that says that lines are straight. But they can't have sharp corners like this, because that would lead to right angles that aren't 90 degrees. And the fourth postulate says all right angles are equal. In essence, what the fourth postulate tells us is that lines don't have to be straight, but they do have to be smooth curves. We can actually take angles between smooth curves the same way we take angles between straight lines. Consider this curve, which is supposed to be the arc of a circle. And then this one. So it may not look like these two curves meet at right angles, but let's dive a little closer. This line is tangent to the first curve at the point of intersection. Tangent means it only touches the curve at one point and doesn't go through the curve, just along it. This horizontal line is tangent to the second curve at the point of intersection. Now, if we forget about the curves and just look at the tangent lines, we see that these are perpendicular lines that form right angles. Going back to the curves, that's how we know that these two curves are perpendicular, even if they don't look it. I bring up this example because it will be important later. There are some non-Euclidean spaces, in fact many non-Euclidean spaces, where arcs of circles are in fact lines under some circumstances. So this will be useful. The last thing I want to note about these first four postulates of Euclidean geometry is that they actually hold for non-Euclidean geometry as well. I kind of tricked you. I know I said we were going to study the postulates of Euclidean geometry, but these are really just the postulates of geometry. They hold for both. So you've actually been doing non-Euclidean geometry this entire time. How does it feel? Moving on, I said there is one more postulate of Euclidean geometry, and it is only in this fifth postulate, the so-called parallel postulate, that Euclidean and non-Euclidean geometry differ. The parallel postulate says, given a line and a point not on the line, there is exactly one line through the given point that is parallel to the given line. I'll say that again. Given a line and a point not on the line, there is exactly one line through the given point that is parallel to the given line. It makes sense when you look at the diagram, but we can already see that this is a little more complicated than our first four postulates. And this isn't even Euclid's original fifth postulate. Euclid's original fifth postulate was, given two lines and a third line which crosses them, if the interior angles on one side of the intersection are smaller than two right angles, then the first two lines must intersect somewhere on that side of the third line. I'll say that again. Given two lines and a third which crosses them, if the interior angles on one side of the intersection are smaller than two right angles, or smaller than 180 degrees, the first two lines must intersect somewhere on that side of the third line. Again, it makes sense if you look at the diagram. If those two angles add up to less than 180 degrees, it means those first two lines must be somehow angled towards one another. So they must intersect somewhere in the distance. And for those of you keeping score at home, it is here in the fifth postulate that we assume that lines are straight. As convincing as the diagram is, this postulate was controversial from the get-go. Many mathematicians thought that this was too complicated to be a postulate. Remember, you want to keep your postulates as simple as possible, and this one isn't that. Some people said we should be able to prove this from the first four postulates, and some mathematicians said, no, we do need a fifth postulate, but let's make it something simpler than this. And they did make a little bit of progress on that. I do think that this fifth postulate is simpler than this one. And I will leave it as an exercise to the reader, as we say in mathematics, to prove that these two are logically equivalent. They are. But simplifying the parallel postulate wasn't enough for some mathematicians. For literally over 2,000 years, people tried to prove the parallel postulate from the first four. One of the things they tried is something called a proof by contradiction. You want to prove that something's true. So first you assume that it's false, and then derive some kind of contradiction. If you've arrived at a contradictory result, your assumption must be wrong, which means that thing you wanted to prove must be true. In this case, here's how it goes. First, assume the parallel postulate is false. Then, derive a falsehood, that is, something that contradicts one of the first four postulates. Well, since you derived something wrong, your assumption must be wrong, which means the parallel postulate must be true. This is how geometers first started experimenting with a world where the parallel postulate isn't true. It's ironic. The first people to study non-Euclidean geometry were actually trying to prove that it didn't exist. But they couldn't do it. If you assume that the parallel postulate is wrong, no matter how hard you look, you won't find something that contradicts the first four postulates, because there isn't a contradiction. The fifth postulate doesn't follow from the first four. It doesn't have to be true. If you assume the fifth postulate as Euclid wrote it, you get Euclidean geometry, the geometry we all know and love. But if you assume something else, you get something else. You get non-Euclidean geometry. So what would it mean for the parallel postulate to be false? Well, remember, the parallel postulate says, given a line and a point not on the line, there is exactly one line through the given point parallel to the given line. If we're going to assume that the parallel postulate is false, there are two distinct possibilities. We could assume there are no lines through the given point parallel to the given line, or we could assume there are two or more. These three logically distinct parallel postulates give rise to three different geometries. If we use the middle column to complete the parallel postulate, as we already know, we get Euclidean geometry. If we use the left column, we get a non-Euclidean geometry called elliptical geometry. If we use the right column, we get a different non-Euclidean geometry called hyperbolic geometry. In the next two videos, we'll discuss elliptical and hyperbolic geometry respectively, and explore a world in which the parallel postulate isn't true. Thanks for watching.